Somewhere in the vast darkness of space, an invisible force is pulling us toward the unknown. Picture this: every galaxy around us, including our own Milky Way, is caught in a cosmic current, drifting toward something we can't see. This isn't science fiction. It's one of the universe's most baffling mysteries, a phenomenon so immense it defies easy explanation. Scientists call it the Great Attractor, and despite decades of research, its true nature remains shrouded in secrecy. Think about that for a moment. Our entire galaxy, with its hundreds of billions of stars, is being drawn towards something we still don't fully understand. What could possibly have that kind of power? The story of the Great Attractor begins with a simple observation: galaxies aren't just drifting randomly through space. Instead, they're moving in a coordinated flow, like leaves caught in a gentle but relentless river. At first, astronomers assumed this motion was due to nearby clusters of galaxies, the usual suspects when it comes to gravitational influence. But as they mapped the cosmos in greater detail, they realized something far stranger was at work. There had to be something massive out there, something hidden behind the thick dust and stars of our own galactic neighborhood, pulling everything toward it with irresistible force. The numbers were staggering. This unseen anomaly had the mass of tens of thousands of Milky Ways, yet it left no visible trace. How could something so enormous stay hidden for so long? That's the question we're going to explore today. From the groundbreaking discoveries that first hinted at the Great Attractor's existence to the cutting-edge technology now helping us peer through the cosmic veil, we're about to uncover the secrets of this gravitational giant. Along the way, we'll confront mind-bending theories, from dark matter's role in this cosmic tug-of-war to the possibility that the Great Attractor might not be a single object at all, but part of something even larger. This isn't just a story about distant galaxies, it's about our place in the universe and the forces that have been shaping our cosmic journey for billions of years. So buckle up. By the end of this video, you'll never look at the night sky the same way again. The discovery of the Great Attractor rewrote our cosmic map in ways nobody expected. Back in the 1970s, astronomers noticed something odd. Galaxies weren't just expanding outward from the Big Bang as predicted. Instead, hundreds of them, including our own Milky Way, were streaming toward a specific region of space at nearly 2 million kilometers per hour. At first, researchers assumed it was a simple case of gravity doing its usual work, with nearby galaxy clusters pulling everything toward them. But when they calculated the numbers, the math didn't add up. The force at play was far stronger than anything visible could explain. This gravitational anomaly lies roughly 250 million light-years away, hidden behind the dense stars and dust of our galaxy's own plane, an area so obscured, astronomers call it the Zone of Avoidance. Imagine trying to spot a distant lighthouse through a thick, swirling fog. That's the challenge scientists faced. Early observations pointed toward the Norma cluster, a massive gathering of galaxies, but even its immense gravity couldn't account for the sheer scale of the attraction. The Great Attractor wasn't just pulling a few galaxies, it was bending the motion of an entire supercluster, a structure spanning hundreds of millions of light-years. So what's really out there? One leading theory suggests the Great Attractor might be the heart of the Laniakea supercluster, a sprawling web of galaxies that includes our own Milky Way. Picture a colossal cosmic watershed where galaxies flow like rivers toward a central valley. But here's the twist: even Laniakea's combined mass might not fully explain the phenomenon. That's where dark matter enters the story. This invisible, mysterious substance, which makes up about 85% of the universe's mass, could be amplifying the gravitational pull in ways we're still struggling to measure. Yet some researchers suspect the truth goes deeper. Recent studies reveal the Great Attractor might not be the final destination at all. Instead, it could be just one stop on a far grander journey with an even more massive structure dubbed the Shapley Attractor lying beyond it, tugging everything toward its grasp. This cosmic tug-of-war hints at layers of gravitational influence we've only begun to map. Every answer leads to new questions, peeling back the universe's secrets one layer at a time. The deeper we look, the clearer it becomes the Great Attractor isn't just a curiosity. It's a reminder of how much we still don't know about the forces shaping our universe. From dark matter's ghostly grip to the possibility of unseen superstructures, this mystery challenges us to rethink the very fabric of space itself. And with new telescopes peering through the Zone of Avoidance, we might finally be on the verge of uncovering what's been pulling us toward the unknown all along. 600 kilometers per second, that's the breathtaking speed at which our Milky Way, along with the entire local group of galaxies, is being pulled toward the Great Attractor. To put that into perspective, at that velocity, you could travel from Earth to the Moon in just about 10 minutes. But what's behind this relentless motion? Gravity, of course, but not just any gravity. This is the pull of something so massive, so densely packed with matter, that it bends the very fabric of space around it, steering entire galaxies like ours along invisible highways. The Shapley Supercluster, one of the most colossal structures in the observable universe, plays a part in this cosmic tug-of-war. Located about 650 million light-years away, it's a gravitational heavyweight, dense with galaxies and dark matter. Yet even Shapley's immense influence can't fully account for the sheer force drawing us toward the Great Attractor. So what's tipping the scales? The answer lies in the way these massive structures interact, creating a sort of cosmic domino effect. Picture a series of waterfalls, each one feeding into the next, with the Great Attractor acting as the central basin, gathering the flow of galaxies from across the universe. To map this unseen force, astronomers rely on two key tools, a redshift data and the cosmic microwave background. Redshift, the stretching of light waves as galaxies move away from us, reveals not just their speed but their direction, painting a picture of the gravitational currents shaping their paths. Meanwhile, the cosmic microwave background, the faint afterglow of the Big Bang, holds tiny temperature fluctuations that hint at the distribution of matter, both seen and unseen, across the cosmos. Together, these clues form a roadmap of our galaxy's journey, showing how the Great Attractor bends the paths of everything around it. But here's where things get even more fascinating. The Great Attractor isn't just pulling us, it's part of an intricate web of motion, a celestial choreography involving thousands of galaxies. Recent simulations suggest that this dance isn't random but follows vast filaments of dark matter, threads of an invisible cosmic skeleton that guide the flow of galaxies across unimaginable distances. Our Milky Way's path, then, isn't just a straight line toward a single point. It's a winding trajectory shaped by the gravitational whispers of countless structures, each adding its own subtle nudge to our journey. This realization transforms how we see our place in the universe. We're not just passive observers floating through space, we're participants in a grand, dynamic system, one where even the emptiest voids play a role in shaping the motion of galaxies. And as telescopes grow more powerful, peeling back the layers of dust obscuring the Great Attractor, we edge closer to understanding the true nature of this cosmic enigma. What we've uncovered so far is just the beginning. The deeper we look, the more we see that our galaxy's story is woven into something far greater, a story written in gravity, dark matter, and the invisible forces that bind the universe together. One of the most frustrating things about studying the Great Attractor is that we can't just point a telescope at it and see what's there. Imagine trying to solve a murder mystery where the prime suspect is hiding behind an impenetrable curtain. That's essentially the challenge astronomers face. The culprit here is our own galaxy. The Milky Way's dense central plane, packed with gas, dust, and countless stars, blocks our direct line of sight to the Great Attractor's location. It's like standing in a crowded room, trying to spot someone on the other side while dozens of people keep crossing in front of you. But scientists aren't easily deterred. When visible light fails, they turn to other wavelengths. Infrared telescopes like NASA Spitzer or the James Webb Space Telescope can peer through the cosmic dust, capturing heat signatures from objects hidden behind the Milky Way's glare. Radio telescopes such as the Parkes Observatory in Australia detect signals that slip past the interference, revealing clusters of galaxies huddled in the Great Attractor's vicinity. These observations confirm there's a lot of mass. They're huge galaxy clusters like Norma and hundreds of others. But here's the catch: even combined, their gravity doesn't fully explain the immense pull we're experiencing. This discrepancy has led to some fascinating theories. Could dark energy, the mysterious force accelerating the universe's expansion, be playing an unexpected role in this region? Or perhaps the Great Attractor isn't just a cluster of galaxies but a relic from the universe's infancy, a dense knot in the cosmic web left over from the Big Bang, where matter clumped together more tightly than anywhere else. Some simulations even suggest it might be part of a vast, interconnected network of superclusters, with gravity funneling galaxies toward it like water spiraling down a drain. Yet with every answer comes new questions. If the Great Attractor is really just a collection of galaxies, why does its gravitational influence extend so much farther than expected? And if dark matter is amplifying its pull, what's the exact distribution of this invisible substance in that region? The more we learn, the clearer it becomes that this cosmic mystery is far from solved. But one thing's certain: the Great Attractor isn't just hiding behind the Milky Way by chance. Its concealment is a reminder of how much of the universe remains unseen, waiting for the right tools and the right minds to bring it into the light. Dark matter might be the universe's best-kept secret, and yet it could hold the answer to the Great Attractor's immense gravitational pull. Think of it like this: if the cosmos were a grand theater, dark matter would be the hidden stagehands, unseen but orchestrating every movement behind the scenes. We can't see it directly. It doesn't glow, reflect, or absorb light, but its presence is undeniable, bending the paths of galaxies like ours with an invisible hand. When astronomers first mapped the Great Attractor's gravitational influence, they hit a snag. The visible matter, galaxies, gas, dust just didn't add up to enough mass to explain the staggering pull. That's where dark matter steps in. Picture a vast cosmic spiderweb, its threads made of this mysterious substance stretching across the universe. Where these filaments intersect, they create dense knots, regions where gravity grows strong enough to reel in entire galaxies. The Great Attractor might sit at one of these intersections, a gravitational hotspot in the dark matter web. Computer simulations paint an even more fascinating picture. When scientists model the universe's growth, they find that dark matter doesn't spread evenly. Instead, it clumps into intricate structures, forming a skeleton that visible matter, galaxies and clusters, simply drapes itself over. These simulations show galaxies flowing along dark matter filaments like water through riverbeds, all converging toward massive nodes. If the Great Attractor is one of these nodes, it would explain why galaxies from all directions seem drawn to it, as if caught in a cosmic current. But here's where things get even more intriguing. Dark matter doesn't just amplify the Great Attractor's pull, it might also explain why this region behaves differently than expected. Some theories suggest that dark matter could be distributed in a way that creates a gravitational lens, bending and magnifying the attraction far beyond what visible matter alone could achieve. It's like adding hidden weights to a scale, tipping the balance in ways we're only beginning to measure. Yet dark matter isn't the only player in this cosmic puzzle. Some researchers speculate that the Great Attractor's pull might be supercharged by something even more elusive: dark energy, the force accelerating the universe's expansion. Could these two invisible phenomena be working in tandem, shaping the motion of galaxies on scales we've barely begun to comprehend? The interplay between dark matter's pull and dark energy's push might hold clues to why the Great Attractor's influence stretches so far. As we piece together this cosmic jigsaw, one thing becomes clear: the Great Attractor isn't just a destination. It's a window into the hidden architecture of the universe, a place where dark matter's secrets might finally come to light. And with every new observation, every sharper image from telescopes piercing through the Milky Way's veil, we edge closer to understanding the true nature of the force guiding our galaxy's journey. The answers won't just rewrite textbooks, they'll reveal how deeply interconnected our universe really is. The Norma cluster and the Hydra Centaurus supercluster have long been prime suspects in the mystery of the Great Attractor's gravitational pull. These colossal gatherings of galaxies packed with stars, gas, and dark matter certainly exert an immense force, but when astronomers crunched the numbers, they hit a wall. Even combined, their mass fell far short of explaining the cosmic tug we're experiencing. It's like discovering a whirlpool in the ocean, only to realize the currents feeding it extend far beyond anything visible on the surface. This discrepancy led scientists to a groundbreaking realization. What if the Great Attractor isn't just a cluster or even a supercluster, but something far more expansive? Enter the Laniakea supercluster, a structure so vast it redefines our understanding of cosmic geography. Stretching over 500 million light-years, Laniakea, Hawaiian for immense heaven, is a sprawling network of galaxy filaments, with the Great Attractor sitting near its gravitational center. Picture a colossal tree, its roots and branches weaving through space, and our Milky Way as just one leaf among thousands, drifting toward the trunk. Here's where things get mind-bending. Laniakea isn't just a random assortment of galaxies. It's a dynamic, flowing system, with entire superclusters moving like rivers toward a common basin. The Great Attractor acts as the pivot point, the place where these cosmic currents converge. But even Laniakea's staggering scale might not tell the whole story. Some researchers suggest the Great Attractor could be part of an even larger gravitational hierarchy, a nesting doll of superclusters influencing one another across mind-numbing distances. This idea reshapes how we see our galactic neighborhood. For decades, we thought of the Virgo supercluster as home, a modest grouping of galaxies including our own. But Laniakea reveals we're part of something far more interconnected, a web where the tug of distant structures shapes our galaxy's path. It's humbling to realize that the Milky Way's journey isn't just a solo voyage but part of a grand, universal dance, choreographed by gravity on scales we're only beginning to map. Yet the puzzle isn't complete. If Laniakea is the stage, what hidden forces are directing the play? Dark matter's invisible threads likely weave through this supercluster, amplifying the Great Attractor's pull in ways we can't yet see. And beyond Laniakea, other titanic structures like the Shapley Supercluster may be adding their own gravitational whispers to the mix. The deeper we look, the more we realize the Great Attractor isn't just a destination, it's a signpost in a universe far more complex and interconnected than we ever imagined. This revelation isn't just about solving a cosmic mystery. It's about perspective. For all our technological advances, we're still learning to read the universe's grand map, one gravitational clue at a time. And as we peer deeper into the cosmos, each discovery reminds us that the forces shaping our galaxy's journey are woven into a tapestry far larger than we've yet dared to dream. While the Great Attractor has captivated astronomers for decades, there's another gravitational behemoth lurking even farther in the cosmic shadows, the Shapley Supercluster. Imagine two celestial giants, each with an armada of galaxies at their command, locked in a silent struggle for dominance across hundreds of millions of light years. This isn't just a battle of mass and gravity. It's a cosmic dance that could redefine our understanding of how the universe structures itself on the grandest scales. Located roughly 650 million light-years from Earth, the Shapley Supercluster isn't just big, it's the most massive known concentration of galaxies in the observable universe. Picture a sprawling metropolis of stars and dark matter, so dense that its gravitational pull can warp the trajectories of galaxies halfway across the cosmos. While the Great Attractor tugs at our Milky Way with undeniable force, Shapley's influence might be the hidden hand shaping the broader flow of our entire galactic neighborhood. Scientists now suspect these two titans aren't acting independently but are part of an intricate gravitational hierarchy, each exerting its own pull while contributing to a larger, interconnected system. The relationship between these superclusters is anything but straightforward. Think of it like a game of cosmic chess, where every move, every shift in mass ripples across the universe. The Great Attractor might dominate our local region, but Shapley's sheer scale suggests it could be the ultimate puppet master, subtly steering the motion of everything around it, including the Great Attractor itself. Recent studies reveal that galaxies aren't just flowing toward one or the other. They're caught in a delicate balance between these competing forces, their paths tracing the invisible contours of gravity's battlefield. Mapping this interplay hasn't been easy. To unravel the mystery, astronomers rely on painstaking observations of galaxy motions, teasing apart the subtle differences in their velocities to determine which supercluster holds more sway. What they've found is astonishing. While the Great Attractor's pull is strong, Shapley's gravitational reach might extend even farther, acting as the anchor point for an entire cosmic watershed. This realization flips the script on earlier assumptions. The Great Attractor isn't necessarily the final destination. It could be more like a waypoint, a stepping stone in a much longer journey dictated by Shapley's overwhelming gravity. But here's where the plot thickens. The universe isn't just a static arena where these superclusters passively exert their pull. Dark energy, the mysterious force accelerating the expansion of space itself, adds another layer of complexity. As the cosmos stretches, the distances between these colossal structures grow, subtly altering the balance of their gravitational influence. Some theories suggest that over billions of years, dark energy might weaken Shapley's grip, allowing other superclusters to rise in prominence. It's a reminder that the universe is anything but static. It's a dynamic, ever-changing stage where gravity and expansion wage an eternal tug-of-war. What does this mean for our Milky Way's future trajectory? While we're currently caught in the Great Attractor's pull, the long-term forecast might see Shapley playing an even greater role in steering our path. Simulations show that as the universe evolves, the collective gravity of superclusters like Shapley could become the dominant force, redirecting galaxies onto new courses over timescales that dwarf human history. This isn't just academic curiosity, it's a glimpse into the forces that will shape our corner of the cosmos for eons to come. The story of these two superclusters isn't just about gravity, it's about perspective. For centuries, we saw the universe as a static backdrop with stars and galaxies fixed in place. Now we know better. The cosmos is alive with motion, a vast network of influences stretching across unimaginable distances. And as we continue to map these hidden currents, each discovery peels back another layer of the universe's grand design, revealing just how small and how profoundly connected we really are. Picture the universe not as a static expanse, but as a living, flowing entity where galaxies drift like leaves on a cosmic river, pulled by currents we're only beginning to chart. These currents, known as cosmic flows, reveal a hidden architecture to the cosmos, a web of gravitational pathways that guide everything from tiny dwarf galaxies to colossal superclusters. At the heart of this vast network lies the Great Attractor, a gravitational nexus where these rivers of matter converge, bending the trajectories of countless galaxies, including our own. What makes these cosmic flows so remarkable isn't just their scale, it's how they serve as a roadmap to the universe's hidden structure. By meticulously tracking the motion of galaxies, astronomers have uncovered a startling truth. Galaxies don't just move outward from the Big Bang in a uniform expansion. Instead, they're tugged by the gravity of nearby superclusters, diverted into streams and eddies that trace the contours of dark matter's invisible scaffolding. It's as if the universe has its own circulatory system, with galaxies flowing along filaments of dark matter like blood cells through veins. The Great Attractor sits at a pivotal intersection in this cosmic highway. Imagine a bustling city where roads from all directions meet. Except here, the roads are made of gravity, and the travelers are entire galaxies. Recent studies suggest this region isn't just pulling matter inward, but also redistributing it, funneling galaxies toward even larger structures like the Shapley Supercluster farther downstream. This dynamic reshapes our understanding of cosmic motion. Rather than a simple tug-of-war between two superclusters, we're seeing a hierarchy of influences, where local flows feed into grander currents, all orchestrated by gravity's unrelenting grip. Mapping these flows isn't just about plotting points in space, it's detective work on a galactic scale. Astronomers rely on two key clues: redshift and peculiar velocities. Redshift tells us how fast a galaxy is moving away from us due to the universe's expansion, but peculiar velocities reveal the subtle deviations caused by nearby gravitational pulls. Combine millions of these measurements, and patterns emerge: rivers of motion that betray the presence of unseen mass. Some of these flows stretch over hundreds of millions of light years, weaving a tapestry so vast it challenges our perception of distance and time. Yet for all we've uncovered, mysteries remain. Why do some galaxies move faster than the flows predict? Could there be even larger structures beyond our current observational horizon, tugging at the edges of the known universe? Each new map deepens the intrigue, revealing wrinkles in the cosmic fabric that hint at forces we've yet to name. What's clear is this: the Great Attractor isn't an isolated phenomenon. It's one piece of a puzzle that spans the cosmos, a puzzle we're only beginning to assemble. And with every galaxy traced, every current mapped, we're not just learning where we're headed, we're uncovering the hidden blueprint of the universe itself. The universe is caught in an epic struggle between two invisible giants, one pulling everything together, the other tearing it all apart. On one side, the Great Attractor's immense gravity tugs galaxies into its orbit, weaving them into vast cosmic currents. On the other, dark energy pushes space itself outward, accelerating the universe's expansion with relentless force. This isn't just a theoretical clash, it's a battle that will determine the fate of everything we see. To understand this cosmic tug-of-war, let's break down the players. The Great Attractor operates like a gravitational anchor. its pull sculpting the motion of galaxies across hundreds of millions of light years. Dark energy, meanwhile, behaves like an anti-gravity force, stretching the fabric of space so fast that distant galaxies will one day vanish beyond our horizon. What makes this duel so fascinating is the imbalance between them. Right now, dark energy is winning. The universe's expansion is speeding up, not slowing down. But here's the twist. In regions like the Great Attractor's domain, gravity fights back with surprising strength. Imagine two teams in a never-ending game of tug-of-war, but the rope itself is growing longer as they pull. That's essentially what's happening on a cosmic scale. While dark energy dominates the universe's overall expansion, dense superclusters like the Great Attractor create localized pockets where gravity still holds sway. These regions become islands of structure in an ever-expanding sea, where galaxies continue to cluster rather than drifting apart. The question isn't just who wins, it's whether these gravitational strongholds can resist the tide indefinitely. Recent simulations reveal an even more complex picture. Dark energy doesn't just stretch space uniformly, it interacts with matter in ways that amplify its effects over time. As the universe expands, matter spreads thinner, weakening gravity's grip while dark energy's influence grows stronger. Yet in superclusters where matter remains densely packed, gravity's hold might persist far longer than elsewhere. This could mean the Great Attractor and structures like it become cosmic relics, the last bastions of order in a universe increasingly dominated by emptiness. But there's another possibility, one that turns our expectations upside down. Some theories suggest dark energy's strength might not be constant. If it evolves over time, gravity could stage a comeback, slowing or even reversing the expansion in regions where matter is concentrated. While this scenario remains speculative, it hints at a universe where the balance between these forces shifts in unpredictable ways. The Great Attractor, then, isn't just a curiosity. It's a testing ground for understanding whether gravity can carve out exceptions to dark energy's rule. What does this mean for the distant future? If dark energy continues its dominance, the Great Attractor's influence will eventually be overcome. Galaxies now flowing toward it will be yanked apart by expansion, their motion rewritten by forces far stronger than gravity. But if superclusters can maintain their cohesion, they might endure as the last vibrant corners of an otherwise fading cosmos. Every observation we make, every galaxy's path we trace brings us closer to answering the ultimate question. Will the universe end in a cold, lonely drift, or will gravity's fingerprints remain, etched into the fabric of space itself? The Great Attractor's story is more than a scientific puzzle. It's a reminder that the universe is dynamic, unpredictable, and full of surprises. As we peer deeper into its mysteries, we're not just mapping the cosmos. We're uncovering the rules of a game played on the grandest stage imaginable, where the stakes are nothing less than the fate of everything. X-ray astronomy has become our secret weapon in piercing the Great Attractor's veil. Unlike visible light, which gets swallowed by the Milky Way's dust, X-rays slice through the cosmic fog like a searchlight, exposing the violent, high-energy processes hidden behind it. When NASA Chandra X-ray Observatory turned its gaze toward this mysterious region, it didn't just find a few stray galaxies, it uncovered a celestial battlefield. Superheated gas swirling at millions of degrees revealed the fingerprints of immense gravitational forces at work. These aren't just random pockets of energy, they're cosmic breadcrumbs leading us straight to the heart of the mystery. The real breakthrough came when Chandra detected vast clouds of this scorching gas, stretching across millions of light years. Gas this hot doesn't exist in isolation. It's the signature of something massive, something capable of heating interstellar material to temperatures rivaling the sun's core. Follow-up observations pinpointed the source: sprawling galaxy clusters previously obscured by the Milky Way's dust, each one a gravitational powerhouse in its own right. But the plot thickened when astronomers noticed something odd. The gas wasn't just sitting still. It was moving, caught in turbulent currents shaped by collisions between clusters, as if entire galaxies were caught in a cosmic whirlpool. This turbulence tells us something crucial about the Great Attractor's nature. Galaxy clusters don't just bump into each other randomly. They're drawn together by gravity, merging over billions of years to form even larger structures. The X-ray data suggests we're witnessing this process in action, with multiple clusters converging toward a common center of mass. It's like watching rivers of galaxies flow into a gravitational maelstrom, their collisions heating the gas to unimaginable temperatures. These observations finally gave scientists a way to weigh the Great Attractor indirectly by measuring how much mass it takes to create such violent motion. The numbers were staggering, far exceeding what visible matter alone could account for. But the surprises didn't stop there. Nestled within these clusters, Chandra spotted another clue: supermassive black holes, some of the most energetic in the known universe. These aren't the quiet, dormant giants like Sagittarius are at our galaxy's center. These are active monsters, devouring matter and spewing jets of radiation that stretch for thousands of light years. Their presence adds another layer to the Great Attractor's gravitational pull, as their colossal mass, millions or even billions of times heavier than our Sun, contributes to the region's overall density. Yet even these black holes, as immense as they are, can't fully explain the scale of the attraction. What makes X-ray observations so transformative is how they reveal the invisible scaffolding of the cosmos. The hot gas maps out the distribution of both ordinary matter and the unseen dark matter that binds it together. By tracing its glow, astronomers have reconstructed a 3D portrait of the Great Attractor's realm, showing how mass is concentrated in ways optical telescopes could never detect. It's like using thermal imaging to find hidden structures behind a wall, except here, the wall is the Milky Way's disk, and the structures are the building blocks of the universe itself. These discoveries have reshaped the search for answers. The Great Attractor isn't a single, monolithic object, but a complex web of galaxy clusters, black holes, and dark matter, all interacting in a gravitational dance we're only beginning to decode. With each new X-ray observation, the puzzle becomes clearer and the universe more astonishing. What once seemed like a singular anomaly now looks like a crossroads of cosmic forces, a place where the visible and invisible worlds collide. And as our telescopes grow sharper, we're not just solving a mystery, we're rewriting the map of our cosmic neighborhood. Hidden behind the Milky Way's crowded star fields and swirling dust clouds lies one of astronomy's greatest frustrations, the Zone of Avoidance. This isn't just a minor inconvenience, it's a vast, opaque curtain draped across 20% of the night sky, blocking our view of countless galaxies beyond. The cruel irony: some of the universe's most intriguing mysteries, including the Great Attractor, lurk right behind this cosmic blind spot. Imagine trying to study a city's skyline while standing in the middle of a dense forest. No matter how hard you squint, the trees keep blocking your view. That's precisely the challenge astronomers face when probing this forbidden zone. For centuries, this region remained a literal blank spot on our cosmic maps. Traditional optical telescopes, designed to capture visible light, simply couldn't penetrate the Milky Way's thick disk of gas and dust. Every photon attempting to reach us from the other side gets scattered or absorbed, like sunlight fading through storm clouds. Early astronomers assumed there was simply nothing out there, a void in the cosmos. But as technology advanced, hints emerged that this empty zone was anything but. The gravitational tug on nearby galaxies betrayed the presence of something massive, something hidden. The Great Attractor wasn't just obscured by chance, it was perfectly positioned behind the one place in the sky we couldn't see. Breaking through this barrier required a revolution in how we observe the universe. When visible light fails, astronomers turn to wavelengths that slice through the cosmic fog: infrared, radio, and X-rays. Infrared telescopes like NASA Spitzer and the James Webb Space Telescope detect heat signatures from objects invisible to optical instruments, revealing galaxies normally lost in the glare. Radio telescopes, including the Parkes Observatory in Australia, capture longer wavelengths unaffected by dust, uncovering hundreds of previously hidden galaxies in the Zone of Avoidance. Each new detection paints a clearer picture of the Great Attractor's neighborhood, proving this region isn't empty at all. It's teeming with cosmic activity we've been missing for generations. Perhaps the most dramatic breakthroughs have come from X-ray observations. Hot gas surrounding galaxy clusters emits X-rays that pierce through the Milky Way's obstruction like headlights through fog. NASA Chandra X-ray Observatory has mapped vast structures in this forbidden zone, including the Norma cluster, a dense gathering of galaxies contributing to the Great Attractor's pull. These observations reveal something startling. What we once thought was a single mysterious force is actually a complex network of galaxy clusters, supermassive black holes, and dark matter, all tangled together in a gravitational knot. Yet, even with these technological leaps, the Zone of Avoidance still guards its secrets fiercely. Some areas remain so dense that not even X-rays can penetrate fully, leaving gaps in our understanding. New instruments, like the upcoming Square Kilometre Array radio telescope, promise to push further into this cosmic frontier, potentially uncovering structures we've never imagined. Every time we develop a new way to peer through this celestial veil, the universe rewards us with fresh surprises: galaxies where we expected none, clusters more massive than predicted, and gravitational anomalies that challenge our models. This relentless pursuit speaks to something deeper than scientific curiosity. The Zone of Avoidance isn't just an observational hurdle. It's a reminder of how much we still don't know about our own cosmic backyard. For all our technological prowess, a significant slice of the universe remains hidden in plain sight, its mysteries waiting just beyond our current reach. But with each technological breakthrough, the veil gets thinner, the blind spot smaller, and as we continue to chip away at this last great frontier of galactic exploration, we're not just solving the mystery of the Great Attractor, we're rewriting our place in the cosmos. The next generation of telescopes is about to tear open the cosmic curtains hiding the Great Attractor's secrets. Leading the charge is the James Webb Space Telescope, with its infrared eyes designed to cut through the Milky Way's dust like a scalpel. Unlike Hubble, which struggled to see past the Zone of Avoidance, Webb's heat-sensitive instruments can detect galaxies obscured for centuries, their faint glow escaping the dust that smothers visible light. Already, early observations hint at previously unseen galaxy clusters lurking behind our galactic plane structures that could explain why the Great Attractor's pull is so much stronger than its visible mass suggests. But Webb isn't working alone. On the ground, the Square Kilometre Array, a sprawling network of radio antennas spanning 2 continents, will map the universe with unprecedented precision. Radio waves ignore interstellar dust entirely, allowing this megatelescope to trace the motions of hydrogen gas in galaxies hidden deep within the Zone of Avoidance. Together, these instruments don't just add pieces to the puzzle, they hand us an entirely new box. What makes this technological leap so transformative isn't just sharper images, it's the ability to see the invisible scaffolding of the cosmos. Dark matter, which makes up most of the Great Attractor's mass, doesn't emit light, but its gravitational effects ripple through the motion of galaxies. By combining Webb's infrared data with the square kilometer array's velocity maps, astronomers can reconstruct the dark matter web threading through this region, revealing where its filaments knot together into gravitational anchors. It's like using sonar to map the ocean floor. We're not seeing the mass directly, but we're watching how everything else moves in response to its pull. Early simulations suggest the Great Attractor might sit at a crossroads of these dark matter rivers, a confluence of cosmic currents we've barely begun to chart. Yet the most exciting possibilities lie in the unexpected. Every time humanity builds a telescope capable of seeing farther, we stumble upon phenomena that defy our models. When the Hubble Deep Field first peered into empty space, it revealed thousands of galaxies where we thought none existed. The Great Attractor's zone could hold similar surprises, perhaps dwarf galaxies swarming like fireflies around an unseen behemoth, or a primordial black hole left over from the universe's birth, far larger than anything predicted. There's even a chance we'll find that the Great Attractor isn't the dominant force we assumed, but a secondary player in a much larger drama, with something even more massive pulling the strings from beyond our current view. The data pouring in over the next decade won't just solve mysteries, it'll create new ones. Each answered question peels back another layer, showing us how much we've underestimated the universe's complexity. And as these telescopes turn their gaze toward the hidden heart of our cosmic flow, one thing becomes clear: the story of the Great Attractor isn't ending. It's just beginning. The Great Attractor isn't just a scientific curiosity, it's a muse for storytellers, a canvas for the wildest cosmic what-ifs. Hollywood and novelists alike have seized its mystery, weaving it into narratives that straddle the line between fact and fiction. Take Interstellar, where the black hole Gargantua's gravitational pull echoes the unseen force of the Great Attractor, bending time and space in ways that feel eerily plausible. While the film took creative liberties with physics, its portrayal of cosmic forces as both beautiful and terrifying taps into the same awe that drives real-world astronomers to study this phenomenon. Literature dives even deeper. Liu Cixin's The Three-Body Problem trilogy imagines a universe where entire civilizations strategize around the movements of galaxies, treating cosmic flows like chessboards. The Great Attractor's role in these stories isn't just backdrop, it's a character, an enigmatic force that shapes destinies. These fictional takes often exaggerate its power, turning it into a sentient entity or a gateway to other dimensions, but they capture something essential: humanity's instinct to personify the unknown. When science can't yet provide all the answers, art steps in to fill the gaps with wonder. Documentaries, though grounded in reality, are no less dramatic. BBC's Universe series frames the Great Attractor as a cosmic detective story, with scientists piecing together clues like interstellar Sherlock Holmesies. The tension is real. Every new telescope or simulation could either solve the mystery or deepen it. This genre thrives on the same questions that haunt researchers. Is the Great Attractor a flaw in our understanding of gravity? A sign of undiscovered physics, or simply a reminder of how much we've yet to explore? Even video games and music have drawn inspiration. The Mass Effect series whispers about ancient civilizations manipulating galactic motion, while ambient composers like Jean Mitchell Jarre create soundscapes that evoke the eerie pull of unseen forces. These interpretations, though fictional, serve a vital purpose. They make the cosmos feel personal. A black and white graph of galaxy velocities can't compete with the emotional punch of a protagonist staring into the abyss, feeling the universe's tug on their ship or their soul. Yet beneath all the artistic flair lies a kernel of truth. The Great Attractor fascinates because it's real. Unlike purely imagined phenomena, It's out there right now, bending the paths of galaxies, including our own. That duality, scientific fact wrapped in cultural myth, is what keeps it alive in our collective imagination. Whether through a physicist's equations or a filmmaker's lens, the message is the same. The universe is stranger, grander, and more interconnected than we ever dreamed. And as long as the Great Attractor keeps its secrets, we'll keep telling stories about it, each one a love letter to the mysteries that refuse to be solved. While superclusters and dark matter dominate the conversation about the Great Attractor, a handful of scientists are chasing far more radical theories that could rewrite our understanding of gravity itself. Imagine if the Great Attractor isn't a place at all, but a glitch in the fabric of space-time, a cosmic wrinkle left over from the universe's birth. One provocative hypothesis suggests this mysterious pull could stem from a primordial black hole, a relic from the first second after the Big Bang. Unlike the black holes we know, formed from collapsing stars, these ancient behemoths could weigh as much as 1,000 suns or more, scattered across the cosmos like invisible anchors. If one lurks in the Great Attractor's direction, its gravity might explain the anomalous motion of galaxies without needing vast amounts of dark matter. Then there's the quantum gravity angle, a notion that the Great Attractor's pull might reveal where Einstein's theory of relativity breaks down. At extreme scales, some physicists argue, gravity could behave differently, warping space in ways our current equations can't predict. It's like discovering that ocean currents don't just follow the wind but are tugged by hidden underwater forces. A team at the Perimeter Institute has even modeled how quantum fluctuations in the early universe might have imprinted strange gravitational patterns, regions where matter flows against the cosmic grain. If they're right, the Great Attractor could be a fossil from this turbulent era, a gravitational echo of the universe's infancy. But perhaps the most mind-bending idea comes from modified gravity theories, which propose that dark matter itself is a mirage, a placeholder for our incomplete understanding. Proponents like physicist Mordechai Milgrom argue that gravity might strengthen subtly in regions of weak acceleration, like the outskirts of galaxies. Applied to the Great Attractor, this could mean its pull isn't from hidden mass but from gravity's own rules changing over vast distances. It's a contentious view, but one that gains traction every time telescopes fail to find the dark matter concentrations our models expect. Skeptics dismiss these alternatives as fringe, and for good reason. They lack the mountain of evidence supporting dark matter and superclusters. Yet history shows science advances when someone dares to ask, what if we're wrong? The Great Attractor's enigma invites exactly that kind of thinking. Whether it's primordial black holes, quantum gravity, or rewritten laws of physics, each unconventional theory forces mainstream science to sharpen its arguments, test its assumptions, and dig deeper for proof. After all, the universe has surprised us before. And until we peel back the last layer of this mystery, the door stays open for the next Copernican shift in how we see the cosmos. The Great Attractor isn't just a silent force in the cosmos, it's an active sculptor, reshaping galaxies with its relentless gravitational pull. Picture a galactic traffic jam where entire star systems are funneled closer together, their paths altered by an invisible hand. As galaxies converge toward this gravitational epicenter, their individual stories begin to intertwine. Star formation, usually a slow and steady process, gets supercharged in some regions while grinding to a halt in others. Dense clouds of gas compressed by the increasing gravitational tides collapse into new stars at a frenetic pace, igniting bursts of stellar birth that outshine entire galaxies. Meanwhile, other areas are stripped bare, their gas reserves ripped away by tidal forces, leaving behind aging stars with no fuel for renewal. This cosmic rearrangement doesn't just affect stars, it stirs up the supermassive black holes lurking at galactic centers. Normally dormant giants awaken as fresh streams of gas and dust spiral into their grasp, transforming them into blazing quasars. These beacons of energy can outshine every star in their host galaxy, their radiation carving out vast bubbles in surrounding gas clouds. But the Great Attractor's influence goes beyond mere illumination. As galaxies draw nearer, their black holes begin a gravitational dance, circling one another in ever-tightening orbits. Over billions of years, these pairs will merge, sending ripples through space-time itself, gravitational waves that echo across the universe. Collisions are inevitable in this crowded celestial arena. The Milky Way and Andromeda, currently on a slow-motion collision course, will find their fate accelerated as the Great Attractor's pull herds them closer to other galaxies. Imagine two spiral galaxies, each with hundreds of billions of stars, passing through one another like ghostly ships. Their stars rarely collide, but their gas clouds crash together, triggering firestorms of new star formation. Over time, these galactic encounters will erase their elegant spiral arms, leaving behind a single, bloated elliptical galaxy, a cosmic fossil of the Great Attractor's handiwork. Yet the most profound changes might be the ones we can't yet see. Dark matter, which outweighs visible matter 5-to-1, is also being reshaped by this gravitational current. As it clumps and stretches along filaments, it creates invisible scaffolds that guide where galaxies can form and how they move. The local group, our galactic neighborhood, is caught in this flow, its trajectory bending toward an uncertain future. Billions of years from now, the night sky as we know it will be unrecognizable, its familiar constellations replaced by the glow of merged galaxy cores and the glare of newborn stars. What does this mean for life in the Milky Way? While the timescales are too vast for human concerns, the implications are staggering. Planets orbiting stars in quiet galactic suburbs today may one day find themselves near the chaotic centers of merged galaxies, bathed in intense radiation. Yet even in this turbulence, there's a strange beauty, a reminder that the universe is anything but static. The Great Attractor's pull isn't just moving galaxies, it's rewriting their destinies, proving that even the mightiest structures in the cosmos are mere players in a grander, ever-unfolding story. Einstein's equations didn't just revolutionize physics, they gave us the language to decode the Great Attractor's hidden influence. At the heart of general relativity lies a deceptively simple idea. Mass bends spacetime like a bowling ball sinking into a trampoline. The heavier the object, the deeper the dent, and the stronger its gravitational pull on everything nearby. Now scale that up to cosmic proportions. The Great Attractor isn't just a bowling ball, it's a mountain range of mass, warping the fabric of the universe so profoundly that entire galaxies slide toward it like marbles rolling downhill. This cosmic curvature explains why galaxies millions of light-years apart move in sync, their paths dictated by the invisible contours of bent spacetime. Einstein's math predicts that even light itself must follow these curves, a phenomenon we've since confirmed by observing how galaxy clusters bend distant starlight like a prism. When astronomers track the Milky Way's motion toward the Great Attractor, they're essentially mapping the slope of this space-time terrain, measuring how steeply the universe tilts in that direction. The numbers are staggering. The Great Attractor's gravitational well is so deep, it deflects galaxies moving at 2% the speed of light. Yet relativity also introduces a paradox. While the Great Attractor's mass warps spacetime locally, the universe as a whole is expanding, stretched thin by dark energy's repulsive force. Einstein's equations accommodate this tension, revealing how gravity and expansion wage a tug-of-war across cosmic distances. Near massive structures like the Great Attractor, gravity wins, pulling galaxies into its grip. But beyond a certain point, dark energy takes over, accelerating expansion and eventually stretching space-time faster than gravity can counteract it. This delicate balance shapes the fate of everything from individual galaxies to the universe itself. What makes Einstein's framework so powerful isn't just its accuracy, it's its adaptability. When astronomers discovered the Great Attractor's pull exceeded what visible matter could explain, relativity didn't break. Instead, it pointed to hidden players like dark matter, whose gravitational fingerprints fit seamlessly into the equations. Even the strangest cosmic motions, galaxies moving too fast, clusters behaving unpredictably, don't defy relativity. They challenge us to look deeper, to find the missing pieces of the puzzle Einstein's math insists must exist. Today, his legacy lives on in supercomputer simulations that model the Great Attractor's gravitational field down to the finest detail. By feeding relativity's equations into these digital universes, scientists can rewind time, tracing how the Great Attractor's influence grew over billions of years. The simulations reveal a story of cosmic construction, dark matter filaments knitting together, galaxy clusters merging, and gravity sculpting the largest structures in existence. Without Einstein's insights, we'd still be staring at the night sky, wondering why the stars drift where they do. Now, thanks to him, we're not just observers of the cosmos, we're interpreters of its deepest secrets. The universe isn't just expanding, it's doing so at a rate that's sparking one of astronomy's biggest debates. On one side, we have measurements from the cosmic microwave background, the afterglow of the Big Bang, suggesting a specific expansion rate. On the other, observations of nearby galaxies and supernova tell a slightly different story, moving faster than expected. This mismatch, known as the Hubble tension, isn't just a minor discrepancy, it's a cosmic puzzle that could hint at gaps in our understanding of gravity, dark energy, or even the hidden influence of structures like the Great Attractor. At first glance, the numbers might seem close enough to ignore, but in cosmology, even a small disagreement can point to something profound. Imagine setting two ultra-precise clocks side by side, only to find one tick slightly faster over time. You'd suspect a hidden force at work, maybe a subtle temperature difference or a flaw in the mechanism. The Hubble tension is like that, but on a galactic scale. The discrepancy suggests there's either something wrong with our measurements or something missing from our models of how the universe behaves. This is where the Great Attractor enters the conversation. Its immense gravitational pull doesn't just bend the paths of nearby galaxies, it could also subtly alter how we perceive their speeds. Think of it like standing on a moving walkway while trying to judge someone's walking pace beside you. If you don't account for the walkway's motion, your estimate will be off. Similarly, if we're caught in a cosmic current flowing toward the Great Attractor, our local measurements of galactic velocities might need recalibration. The tension could stem from not fully accounting for this regional flow, a gravitational bias skewing our data. Yet the plot thickens when we consider dark energy, the mysterious force accelerating the universe's expansion. If its strength isn't constant, if it varies across space or time, it could explain why distant and nearby regions seem to expand at different rates. Some theories even suggest dark energy interacts differently with matter in overdense regions like the Great Attractor's domain, creating pockets where expansion doesn't follow the universal average. It's as if the universe has multiple gears, shifting speeds depending on where you look. Resolving this tension isn't just about tweaking numbers, it could redefine how we map the cosmos. New telescopes like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope aim to settle the debate with sharper observations of distant supernova and ancient galaxies. Meanwhile, advanced simulations are testing whether the Great Attractor's gravitational wake might be distorting our local measurements more than we realized. Every dataset, every model, brings us closer to answering whether the tension is a measurement glitch, a gravitational illusion, or a sign of physics beyond Einstein's theories. The stakes couldn't be higher. If the discrepancy holds, it might mean our cosmic rulebook is incomplete, that dark energy behaves in ways we haven't imagined, or that gravity itself plays by different rules on vast scales. Alternatively, it could confirm that colossal structures like the Great Attractor have been subtly steering our perceptions all along. Either way, the Hubble tension isn't just a scientific hiccup, it's a beacon, guiding us toward the next frontier in our understanding of the universe. And as we dig deeper, we're not just solving a puzzle, we're rewriting the story of how the cosmos grows, evolves, and surprises us. What if the Great Attractor isn't just a cosmic anomaly, but a window into another universe entirely? Among the most daring theories in modern cosmology is the idea that this mysterious gravitational force could be a ripple from a parallel reality, bleeding into our own. Picture two soap bubbles floating close together, their surfaces nearly touching. Where they press against each other, the membrane between them thins, allowing subtle influences to pass through. If our universe is one of those bubbles, the Great Attractor might mark the spot where a neighboring cosmos exerts its pull, warping spacetime in ways we're only beginning to detect. This isn't pure science fiction. The multiverse hypothesis, long debated in physics, suggests our universe might be one of countless others, each with its own laws and constants. Some versions of string theory even predict higher dimensional brains' cosmic membranes that could brush against one another, transferring energy or gravity across the divide. While we've never observed direct evidence of other universes, the Great Attractor's unexplained mass and gravitational dominance make it a tantalizing candidate for such crossover effects. It's as if we've stumbled upon a cosmic fingerprint smudged on the boundary between realities. Critics argue this idea veers into untestable speculation, and they're not wrong. Without a way to peer beyond our universe's edge, proving a multiverse connection seems impossible with current technology. Yet the same was once said about black holes and gravitational waves, phenomena theorized decades before we could observe them. What makes the Great Attractor so compelling is how it defies conventional explanations. Dark matter and superclusters can account for much of its pull, but the lingering discrepancies leave room for wilder possibilities. If a neighboring universe's gravity were leaking into ours, it would create exactly the kind of localized, intense attraction we're seeing. Philosophers love this idea because it blurs the line between science and metaphysics. If the Great Attractor is truly a multiversal artifact, it challenges our very definition of reality. Are the forces shaping our cosmos purely internal, or could they be influenced by realms beyond our perception? The question isn't just about astronomy, it's about the nature of existence itself. And while we may never get a definitive answer, the act of asking pushes the boundaries of both cosmology and imagination. For now, the multiverse connection remains a fringe theory, overshadowed by more grounded explanations. But science thrives on bold ideas, and the Great Attractor's enigma invites us to think bigger. Whether it's a hidden supercluster, a knot of dark matter, or a gateway to another reality, one thing's certain: the universe is far stranger than we've dared to dream. And sometimes the wildest hypotheses are the ones that lead us to the truth. Deep within the Great Attractor's hidden realm, supermassive black holes may be lurking cosmic anchors with gravity so intense they could single-handedly explain the region's mysterious pull. These aren't just ordinary black holes like the one quietly sitting at the Milky Way center. We're talking about monsters weighing billions of times the mass of our Sun, packed into spaces smaller than our solar system. Their gravitational grip is so powerful, they don't just bend space-time, they twist it into knots, dragging entire galaxies along for the ride. Take the Norma cluster, one of the densest galaxy gatherings near the Great Attractor. At its heart lies a supermassive black hole so energetic, it spews jets of plasma stretching millions of light years into space. If structures like this are common in the Great Attractor's domain, their combined gravity could easily account for the anomalous motion we observe. But here's the catch: black holes this massive don't act alone. They're often surrounded by smaller siblings, a whole hierarchy of dark giants orbiting one another in a gravitational ballet. Together, they form an invisible scaffold, amplifying each other's pull in ways that could mimic the effect of a single, unimaginably large object. Detecting these black holes isn't as simple as pointing a telescope. Unlike stars, they emit no light, only the faint glow of superheated gas spiraling into their grasp, a process that creates X-rays we can sometimes spot. The problem: the Milky Way's dusty disk obscures most of this radiation, leaving us with only fragmented clues. That's why astronomers turn to indirect methods, like tracking the bizarre orbits of stars near suspected black holes or measuring how their gravity lenses distant light. Each observation is a breadcrumb, leading us closer to understanding whether the Great Attractor's core is a single leviathan or a swarm of dark predators. The most tantalizing possibility: a binary black hole system, two supermassive giants locked in a slow death spiral. Such pairs are thought to form when galaxies collide, their central black holes eventually merging in an explosion of gravitational waves. If the Great Attractor hosts one of these rare duos, it could explain why the region's gravity feels so concentrated. Simulations show binary black holes warp spacetime like a spinning top, creating chaotic orbits for nearby stars and gas. This turbulence might even explain the strange X-ray signatures we've glimpsed through the cosmic fog. Yet even if black holes are part of the answer, they're likely just one piece of the puzzle. Their gravity, immense as it is, probably isn't enough to account for the Great Attractor's full influence. That's where dark matter comes in, the invisible glue that binds galaxies together. Combined, these forces could create a gravitational nexus far stronger than the sum of its parts. It's like hearing footsteps in the dark. You might catch glimpses of what's making the sound, but the full picture remains just out of sight. Until we peer deeper into the Great Attractor's hidden heart, the truth will stay locked in the shadows, waiting for the next breakthrough to set it free. Galactic cannibalism sounds like something straight out of a cosmic horror story, but it's a very real process shaping the universe around us. Picture a massive spiral galaxy, its graceful arms stretching across space, slowly tearing apart a smaller neighbor. Over billions of years, gravity does its relentless work, stretching the victim galaxy into streams of stars and gas that swirl like celestial spaghetti around the predator. This isn't just destruction, it's transformation. The larger galaxy grows even more massive, its structure warped by the feast, while the smaller one becomes little more than a ghostly stain in its halo. Now drop this violent dance into the heart of the Great Attractor's domain, where gravity's grip is stronger than almost anywhere else. Here, galaxies aren't just drifting, they're funneled together at incredible speeds, crammed into a cosmic pressure cooker. Collisions that might take eons elsewhere happen faster here, with galaxies merging so frequently that some astronomers call it a galactic demolition derby. The result: super-sized galaxies bloated from countless mergers, their shapes twisted beyond recognition. The Norma cluster, a key player near the Great Attractor, is a prime example. Its central galaxy, Abell 3627, is a monstrous elliptical beast, likely built by swallowing dozens of smaller galaxies over time. But galactic cannibalism isn't just about size, it's about survival of the fittest. Smaller galaxies caught in the Great Attractor's pull don't stand a chance. Their gas, the lifeblood of new stars, gets stripped away by tidal forces or heated to extremes by collisions, snuffing out star formation. Meanwhile, the victors grow so large they dominate their local environment, their gravity dictating the motions of everything around them. It's a hierarchical universe where the biggest structures arise from countless smaller ones falling prey to something greater. What makes the Great Attractor's role so fascinating is how it accelerates this process. Normally, galaxies merge at a leisurely pace, but here, the sheer density of matter cranks everything into overdrive. Computer simulations show that in such extreme environments, mergers happen earlier and more violently than in quieter corners of the cosmos. The Milky Way itself might one day face this fate. As we're pulled deeper into the Great Attractor's influence, our galaxy could eventually collide with Andromeda, then merge with others, until all that remains is a single, featureless elliptical giant, a fossil of the cosmic feast. Yet these cataclysms aren't just destructive, they're creative. When galaxies merge, their gas clouds smash together, triggering fireworks of new star birth. Some of the universe's brightest starburst galaxies, ablaze with young stars, are born from these violent encounters. Even supermassive black holes, once dormant, wake up to devour the fresh influx of material, lighting up as quasars that can outshine entire galaxies. The Great Attractor's environment doesn't just tear galaxies apart, it reshapes them into something new, forging the next generation of cosmic structures. Studying these collisions gives us a front-row seat to the universe's relentless evolution. By observing how galaxies behave in the Great Attractor's grip, we're seeing the future of our own cosmic neighborhood. It's a reminder that the cosmos isn't static. It's a living, changing arena where gravity writes the rules, and even the mightiest galaxies are just players in a game that spans billions of years. The Great Attractor isn't just pulling us toward an unknown destination, it's showing us how the universe builds its grandest designs, one merger at a time. Neutrinos might be the universe's ultimate cosmic spies, silent, nearly undetectable particles slipping through matter like ghosts through walls. Born in the hearts of stars, black holes, and violent galactic collisions, they carry secrets from places light can't escape. And right now, trillions of them are passing through your body every second, untouched and unnoticed. But for astronomers, these elusive particles could be the key to unlocking the Great Attractor's deepest mysteries. Unlike light, which gets swallowed by the Milky Way's dust, neutrinos barrel straight through, untouched by obstacles, delivering pristine information from the hidden realm beyond. The challenge: catching them. Neutrinos barely interact with matter at all. To stand a chance of detection, scientists build colossal traps. Like the Ice Cube Neutrino Observatory, a network of sensors buried deep in Antarctic ice, waiting for the rare moment a neutrino collides with an atom and creates a faint flash of light. It's like trying to hear a whisper in a hurricane, but recent upgrades are turning the tide. Next-generation detectors, like the planned Ice Cube Gen 2 and the Pacific Ocean's P1, will expand the hunt with volumes of sensors so vast they could finally spot neutrinos from the Great Attractor's direction. Why does this matter? Because neutrinos could reveal what's happening in environments too extreme for other messengers. Picture the chaotic core of the Great Attractor, where supermassive black holes shred stars, galaxies collide, and gas heats to temperatures we can't replicate on Earth. These violent processes should spray neutrinos into space like sparks from a forge. If we can trace them back to their source, we might map the attractor's hidden structure for the first time. Some theories even suggest neutrino patterns could expose dark matter's distribution, showing where this invisible substance clumps most densely around the attractor's heart. But the real revolution lies in timing. When a neutrino arrives, it points straight back to its origin, no cosmic dust, no gravitational lensing to distort its path. Pinpoint a flood of neutrinos from the Great Attractor's direction, and you've essentially drawn an X on the cosmic map. Combine that with gravitational wave data and X-ray observations, and suddenly the attractor's secrets start coming into focus. It's like assembling a puzzle where each piece is a different wavelength of the universe's hidden language. Of course, it's not easy. Neutrino astronomy is still in its infancy, and every detection is a triumph against staggering odds. But the potential rewards are cosmic. If successful, this could be our first true glimpse into the Great Attractor's engine room, a place where the universe's most violent and creative forces converge. And as detectors grow more sensitive, we might not just solve one mystery. We could open an entirely new window onto the cosmos, one where even the darkest corners can't hide their secrets forever. The universe isn't just a random scattering of galaxies, it's a meticulously woven tapestry, a cosmic web stretching across unimaginable distances. Picture an enormous spider's silk, threads of dark matter and gas crisscrossing the void, with galaxies strung along them like beads. At the intersections of these filaments, matter piles up, forming dense knots where gravity's grip is strongest. And right at the heart of one such convergence sits the Great Attractor, a gravitational anchor pulling everything toward its hidden core. This web isn't just a poetic metaphor, it's the backbone of cosmic structure. Simulations of the universe's evolution show how tiny fluctuations after the Big Bang grew over billions of years, with gravity amplifying the densest regions into sprawling filaments. The emptier spaces between them became voids, vast cosmic deserts where galaxies are few and far between. The Great Attractor sits where several of these filaments meet, a crossroads in the universe's grand highway system. Galaxies don't just drift aimlessly, they flow along these invisible threads, funneled toward the web's densest nodes like water rushing toward a drain. Mapping this web is like trying to reconstruct a city's subway system while standing on a single platform. We can see the galaxies, the stations, but the tracks themselves are made of dark matter, invisible to our telescopes. To chart them, astronomers rely on the motions of galaxies, tracing their paths to infer the web's hidden architecture. Each galaxy's movement is a clue, a signpost pointing toward the densest regions of the cosmic web. And when you plot enough of them, a pattern emerges, streams of galaxies all flowing toward the Great Attractor, pulled by the web's gravitational currents. What's fascinating is how this web shapes galaxies over time. Those near the filament's intersections, like the Great Attractor's domain, live in a crowded, chaotic environment. Collisions are frequent, gas is stripped away, and star formation runs hot and fast. But galaxies out in the filament's quieter stretches evolve more peacefully, spinning undisturbed for eons. It's the difference between a bustling metropolis and a sleepy countryside, both part of the same universe, but shaped by wildly different surroundings. The cosmic web also solves one of the Great Attractor's biggest puzzles: how something so massive stays hidden. The answer: it's not just one object but a confluence of structures, galaxy clusters, dark matter halos, and swirling gas, all tangled together at a filamentary crossroads. This means the Great Attractor's pull isn't from a single source but from the combined gravity of an entire network, a gravitational ensemble acting in unison. As our telescopes peer deeper into the web, they're revealing just how much we've underestimated its complexity. Some filaments stretch over 1 billion light-years, weaving across the cosmos in delicate, luminous strands. And the Great Attractor, it might not even be the largest node in our cosmic neighborhood. New studies suggest even bigger gravitational hubs lie beyond, their pull subtly steering the web's flow on scales we're only beginning to grasp. Understanding this web isn't just about solving a mystery, it's about seeing the universe for what it truly is. A dynamic, ever-changing network where gravity writes the rules and galaxies are just passengers along for the ride. The Great Attractor isn't an anomaly, it's a landmark in a much larger story, one that's still being written with every new observation, every deeper look into the cosmos' hidden architecture. Time itself bends under the immense gravity of the Great Attractor, stretching and warping like taffy in the hands of a cosmic giant. Einstein's theory of relativity tells us that gravity doesn't just pull on objects, it tugs at the very fabric of time. Near a massive enough structure, clocks tick slower than those farther away, a phenomenon called gravitational time dilation. It's why a clock on Earth's surface runs slightly slower than one in orbit, and why a black hole's crushing gravity can freeze time entirely from an outsider's perspective. Now, imagine that effect scaled up to the Great Attractor's staggering mass. While its gravitational pull isn't as extreme as a black hole's, the sheer volume of matter concentrated there, both visible and dark, could create subtle but measurable distortions in time itself. For a hypothetical observer near the Great Attractor's core, time would crawl compared to someone in intergalactic space. A single second for them might stretch into a fraction longer for us, a difference too small for human perception but detectable with precise enough instruments. Atomic clocks, which lose or gain nanoseconds under Earth's weaker gravity, could theoretically reveal these distortions if placed near the attractor's influence. Even without sending hardware across millions of light-years, astronomers have indirect ways to spot time dilation's fingerprints. Light emitted by galaxies caught in the attractor's grip would redshift slightly more than expected, stretched not just by the universe's expansion, but by the extra time warping effect of extreme gravity. The implications go beyond curiosity. If we could measure this time dilation, it would act as a cosmic scale, weighing the Great Attractor's true mass with unprecedented accuracy. Current estimates rely on the motions of galaxies, which can be skewed by unseen structures or dark matter's uneven distribution. But time dilation depends purely on gravity's raw strength, offering a direct probe into the attractor's hidden heart. It's like deducing a mountain's size not by measuring how far hikers trek around it, but by how deeply it warps the ground beneath it. Yet there's a twist. Time dilation near the Great Attractor isn't just a one-way slowdown, it's part of a larger relativistic tapestry. The region's gravitational pull accelerates galaxies to dizzying speeds, and at those velocities, special relativity kicks in, causing additional time dilation from motion alone. Untangling these effects, gravity's drag versus velocity's stretch, could reveal whether the attractor's core is a single concentrated mass or a diffuse web of dark matter and galaxies. Each scenario bends space-time differently, leaving distinct imprints on passing light and the flow of time. Future telescopes might turn these theories into data. Missions like the Laser Interferometer Space Antenna LISA could detect gravitational waves from merging black holes near the Great Attractor, their signals subtly altered by the region's time-warping gravity. Similarly, ultra-precise pulsar timing arrays networks of spinning neutron stars acting as cosmic metronomes, might catch faint irregularities caused by the attractor's influence. These measurements wouldn't just solve a local mystery, they'd test relativity itself on scales Einstein never imagined, probing whether his equations hold true in the most extreme corners of the cosmos. What makes this so thrilling is the duality of the discovery. Confirming time dilation near the Great Attractor wouldn't just illuminate its secrets, it would prove, once again, that the universe operates by rules both bizarre and beautiful. The same physics that makes GPS satellites correct their clocks for Earth's gravity also governs the motion of galaxies millions of light years away. And if the attractor's time-bending grip defies predictions, that's when things get really interesting. Anomalies here could hint at new physics, from exotic dark matter behaviors to modifications in how gravity works on cosmic scales. Either way, the Great Attractor isn't just pulling galaxies, it's stretching our understanding of reality itself. The universe began not with a bang, but with a whisper, a quantum whisper. In the first trillionth of a second after the Big Bang, when the entire cosmos was smaller than a single atom, unimaginably tiny fluctuations flickered through the primordial soup of energy. These weren't just random blips, they were the seeds of destiny. Billions of years later, those microscopic ripples would grow into the vast cosmic web we see today, with the Great Attractor sitting at one of its most massive knots. It's a staggering thought. The same quantum physics that governs subatomic particles may have set in motion the gravitational behemoth now pulling our galaxy toward oblivion. How does a fluctuation smaller than a proton blossom into a structure weighing tens of thousands of galaxies? The answer lies in inflation, the universe's explosive growth spurt in its first fraction of a second. As space expanded faster than light, those quantum ripples stretched along with it, freezing into faint density variations across the young cosmos. Slightly denser regions pulled in more matter through gravity, growing ever heavier over eons, while emptier patches became the voids we see today. The Great Attractor, then, might trace its lineage back to one particularly pronounced fluctuation, a quantum hiccup that, amplified by inflation, became a gravitational titan. This connection between quantum mechanics and cosmology isn't just poetic, it's measurable. The cosmic microwave background, the afterglow of the Big Bang, bears the imprints of those early fluctuations as subtle temperature variations. Remarkably, the pattern matches predictions from quantum theory with uncanny precision. It's as if the universe left us a fingerprint, and the ridges point straight from subatomic randomness to the Great Attractor's sprawling mass. Simulations show how these tiny seeds could evolve into the cosmic web, with filaments of dark matter funneling galaxies toward nodes like the Attractor with eerie inevitability. Yet mysteries remain. Why did certain fluctuations grow more prominent than others? Could the Great Attractor's unusual density hint at something deeper, a primordial quantum anomaly, or even a rare statistical fluke in the early universe's chaos? Some theorists speculate that exotic phenomena, like cosmic strings or domain walls left over from phase transitions, might have supercharged certain regions. Others suggest the Attractor's position at a web filament crossroads isn't accidental, but a direct consequence of how quantum noise intertwined with dark matter's hidden scaffolding. The real magic lies in the scale. Quantum physics typically operates in a realm far removed from everyday experience. Think electrons tunneling through barriers or particles popping in and out of existence. But the Great Attractor forces us to see the quantum world differently, not as separate from the cosmos, but as its architect. Those fleeting early fluctuations were like strokes on a canvas, invisible at first, but destined to shape a masterpiece spanning hundreds of millions of light years. This revelation blurs the line between the infinitesimal and the infinite. The same math describing electrons' probabilistic behavior also charts the Great Attractor's gravitational dominance. It's a reminder that the universe doesn't compartmentalize, it connects. And as we peer deeper into the Attractor's origins, we're not just tracing the growth of galaxies. We're uncovering how the smallest threads of reality wove the grandest tapestry of all. Dark matter doesn't drift aimlessly through the cosmos, it's sculpted by gravity, drawn toward the universe's most massive structures like iron filings to a magnet. The Great Attractor, with its staggering gravitational pull, doesn't just bend the paths of galaxies, it warps the very distribution of dark matter itself, shaping an invisible landscape that determines where and how galaxies can form. Picture a vast cosmic whirlpool, its currents invisible to the eye but undeniable in their influence. Galaxies aren't just pulled toward the attractor, they're riding atop rivers of dark matter, their motion dictated by the contours of this hidden terrain. The relationship between the Great Attractor and dark matter is a gravitational tango. Dark matter halos, those massive, diffuse clouds surrounding galaxies, are stretched and compressed by the attractor's pull, their shapes distorted like taffy in the hands of a giant. In regions closer to the attractor, these halos grow denser, their increased gravity accelerating star formation and triggering galactic collisions. Farther out, the halos stretch into elongated filaments, threading galaxies together in a web that funnels them toward the attractor's core. This isn't just theoretical observations of galaxy motions, and gravitational lensing reveal dark matter's fingerprints all over these cosmic flows. But here's where it gets even more fascinating. Dark matter doesn't just respond to the Great Attractor's gravity, it amplifies it. The attractor's visible mass, galaxies, gas, and dust can't account for the sheer strength of its pull. It's the dark matter piled deep around this gravitational nexus that supercharges its influence. Simulations show how dark matter clusters around the attractor in a vast, invisible shroud, its gravity reaching far beyond what visible matter alone could achieve. This creates a feedback loop. The attractor's gravity draws in dark matter, which in turn strengthens the attractor's pull, drawing in even more matter. It's a cosmic snowball effect, one that's been rolling for billions of years. The consequences ripple across galactic evolution. Galaxies caught in the attractor's grasp don't just move, they transform. Dark matter's uneven distribution creates pockets of extreme density, where galaxies collide and merge at breakneck speeds. In quieter regions where dark matter thins out, galaxies spin in isolation, their star formation slowing to a crawl. This duality, chaos in the dense zones, calm in the sparse ones, shows how dark matter acts as the universe's ultimate puppeteer, pulling the strings behind everything we see. Yet mysteries linger. Why does dark matter clump so intensely around the Great Attractor compared to other regions? Could there be something unique about this patch of the cosmos, a relic from the universe's birth that seeded extra dark matter here? Or is the attractor simply the most visible knot in a much larger dark matter web, one we've only begun to trace? Every new observation peels back another layer, revealing how deeply dark matter's secrets are tied to the fate of galaxies, including our own. Understanding this dynamic isn't just academic, it's a key to decoding the universe's blueprint. The Great Attractor's sway over dark matter doesn't just shape distant galaxies, it hints at how all structures, from the smallest dwarf galaxies to the largest superclusters, are born and molded. And as we map this hidden interplay, we're not just solving a cosmic mystery, we're learning how the universe builds itself, one invisible thread at a time. Gravitational lensing is nature's magnifying glass, bending the very fabric of light to reveal what lies hidden in the cosmos. When the immense gravity of the Great Attractor warps space-time, it distorts the images of galaxies behind it, stretching them into eerie arcs and smears, like looking at a distant street lamp through a wine glass. These distorted snapshots aren't just cosmic oddities, they're treasure maps. By analyzing how light bends around the attractor, astronomers can trace the invisible scaffolding of dark matter and pinpoint where mass concentrates. even in regions obscured by the Milky Way's dust. It's akin to deducing the shape of a hidden object by studying its shadow. The most striking examples come from galaxy clusters near the attractor's core, like Able 370, where gravitational lensing transforms background galaxies into luminous crescents and rings. Each distortion encodes precise data about the mass responsible for the bending. Supercomputer algorithms then reverse engineer these light paths, reconstructing the attractor's gravitational field in 3 dimensions. The results are staggering. The Great Attractor's mass isn't just concentrated in visible galaxies but extends far beyond, enveloped in a halo of dark matter 10 times more massive than the stars and gas we can see. Without lensing, this hidden bulk would remain a ghost in the equations, but lensing does more than weigh the attractor. It exposes its structure. Some lensed images appear fragmented, a phenomenon called strong lensing, where multiple copies of the same galaxy appear around the attractor's edges like a cosmic hall of mirrors. These duplicates arise because light takes different paths around the gravitational well, arriving at Earth at slightly different times. By comparing these time delays, astronomers can measure the attractor's depth and shape, revealing whether its mass is smoothly distributed or clumped in dense knots. Recent observations hint at the latter, vast subhalos of dark matter swirling within the attractor's grasp, each amplifying its pull like invisible moons around a planet. Weak lensing, a subtler effect, paints the broader picture. Here, background galaxies aren't dramatically warped but subtly stretched, their shapes aligned like iron filings along magnetic lines. By cataloging millions of these tiny distortions, researchers map the attractor's gravitational influence across hundreds of millions of light years. The resulting maps show filaments of dark matter feeding into the attractor, funneling galaxies along highways of gravity. This technique also uncovered something unexpected. The attractor's pull isn't perfectly symmetrical. Its gravity seems lopsided, as if something even larger, perhaps the Shapley Supercluster, is tugging it off-center from behind. Gravitational lensing isn't just a tool, it's a paradigm shift. Traditional astronomy relies on light emitted by objects, but lensing thrives on absence, using the voids and bends to illuminate the unseen. The Great Attractor, once a frustrating enigma, now yields its secrets through the very distortions it creates. And as telescopes like Euclid and the Vera Rubin Observatory come online, their ultra-sensitive lenses will capture fainter, more distant warped galaxies, refining our maps of this cosmic colossus. Every twisted image, every stretched star, is a whisper from the dark, a clue to the forces shaping our galaxy's journey through the universe. Our galaxy's future was supposed to be simple, a slow dance with Andromeda ending in a spectacular merger billions of years from now. But the Great Attractor has rewritten the script. This unseen gravitational giant doesn't just bend the paths of distant galaxies. It's reaching into our own cosmic backyard, subtly tugging at the entire local group with enough force to alter our destiny. The Milky Way and Andromeda may still collide, but the when, where, and how of this celestial tango are now questions with surprising new answers. Current projections show Andromeda barreling toward us at 110 kilometers per second, set to collide in about 4.5 billion years. But those calculations assumed a quiet cosmic neighborhood, free from major gravitational disruptions. Enter the Great Attractor, lurking 250 million light-years away with the mass of tens of thousands of Milky Ways. Its pull is already nudging our local group sideways at nearly 600 kilometers per second, a motion so significant it could bend our merger trajectory like a river changing course around a boulder. Instead of a head-on collision, we might experience a glancing blow, or even a delayed encounter as both galaxies get dragged toward the attractor's hidden realm. The real wild card, dark matter. The Great Attractor's gravitational reach extends far beyond its visible galaxies, courtesy of vast halos of this mysterious substance. As the local group moves through these invisible currents, we might experience tidal forces strong enough to warp our galactic outskirts long before Andromeda arrives. Picture two ships caught in a whirlpool, their approach altered not just by their own engines, but by the swirling water around them. Some simulations suggest the Great Attractor's dark matter web could strip gas from both galaxies during their approach, starving future star formation and leaving behind skeletal structures barely resembling today's spirals. Yet the story doesn't end with a single merger. The Great Attractor's influence ensures our local group won't remain isolated. Over tens of billions of years, we'll likely merge with other galaxy groups along the attractor's inflow, forming a single, bloated elliptical galaxy, a fate shared by most in our cosmic neighborhood. This future conglomerate, sometimes called Milkomda or Milkdromda, won't be the majestic spiral we know today but a featureless giant, its stars redistributed by countless collisions. The night sky for any surviving civilizations would be utterly transformed, with Andromeda's stars fully mixed with our own and new arrivals from smaller galaxies adding to the glow. But here's the twist. The Great Attractor itself isn't stationary. It's being pulled toward the even more massive Shapley Supercluster, meaning our long-term fate might involve joining a river of galaxies flowing toward an even larger cosmic basin. The local group's journey, once thought to be a simple two-galaxy affair, is now revealed as a multi-billion-year odyssey through ever larger gravitational hierarchies. We're not just merging with Andromeda, we're being drafted into a cosmic migration that will eventually see our descendants stellar or otherwise absorbed into one of the universe's largest structures. This revelation changes how we see our place in the cosmos. The Milky Way isn't an island universe but a speck in a vast flow, our motion dictated by forces beyond our immediate horizon. The Great Attractor's pull reminds us that no galaxy, no matter how grand, is truly independent. We're all caught in gravity's web, riding currents set in motion when the universe was young. And as telescopes peer deeper into these hidden flows, each new observation brings us closer to understanding not just where we're headed, but how the universe choreographs its grandest ballets. The cosmic microwave background is more than just a relic of the Big Bang. It's a forensic snapshot of the universe's infancy, holding faint clues to the Great Attractor's ancient origins. Picture this afterglow as a vast cosmic fingerprint. Its subtle temperature variations, warmer red splotches and cooler blue patches, marking where matter was slightly denser or sparser when the universe was just 380,000 years old. Remarkably, some of these primordial hotspots align eerily with the direction of the Great Attractor today, as if the seeds of this gravitational giant were planted in the first moments of creation. These temperature fluctuations, no larger than 1 part in 100,000, might seem insignificant, but gravity works slowly and relentlessly. Over billions of years, those slightly denser regions pulled in more matter, growing like snowballs rolling downhill, while sparser areas became the voids we see today. The Great Attractor likely began as one of these overdense patches, a cosmic lottery winner that amassed more than its share of dark matter and gas. When scientists compare modern galaxy surveys with CMB maps, they find a staggering correlation. The same regions that glow slightly warmer in the microwave background now host superclusters, while cooler patches align with vast cosmic deserts. What makes this connection so profound is the timescale involved. That faint imprint in the CMB traveled for over 13 billion years to reach us, carrying a message from an era when the universe was 1,000 times smaller and 1,000,000,000 times hotter. The matter that would eventually become the Great Attractor was once packed into a volume less than a light year across, smaller than the distance from Earth to its nearest star. Today, that same material sprawls across hundreds of millions of light years, its gravitational influence bending the paths of galaxies halfway across the observable universe. Advanced statistical techniques reveal even deeper layers to this story. By analyzing the CMB's polarization patterns, the way its light waves vibrate in specific directions, researchers can trace how matter flowed in the early universe. Some models suggest the Great Attractor's region experienced faster than average growth, as if it sat at the confluence of multiple cosmic currents from the very beginning. This would explain why it became such a gravitational powerhouse, while other overdense regions evolved into more modest galaxy groups. The CMB's polarization acts like fossilized ripples, preserving the direction and speed of these ancient flows long after the universe's first light faded. Yet mysteries linger. Why did this particular patch grow so dominant? Some theorists propose it benefited from a rare confluence of dark matter filaments, while others speculate quantum fluctuations during inflation might have gifted it extra density. The Planck satellite's ultra-precise CMB measurements even hint at anomalies in this region, subtle asymmetries that could point to physics beyond our current models. Whatever the explanation, the Great Attractor's roots in the CMB remind us that the cosmos doesn't evolve randomly. From quantum seeds to galactic superstructures, the universe builds its grand designs with patient mathematical precision, one gravitational whisper at a time. Long before telescopes revealed the Great Attractor's gravitational pull, humanity sensed invisible forces at work in the cosmos. Ancient Polynesian navigators spoke of mana, a spiritual current guiding stars and canoes alike across the Pacific. The Babylonians charted celestial patterns they believed mirrored divine wills, while Hindu cosmology described a cosmic serpent whose coils shaped the universe's flow. Though these cultures couldn't fathom dark matter or superclusters, their myths captured a profound truth: the universe moves to hidden rhythms, and we are caught in its tide. This interplay of myth and science becomes even more striking when we consider how modern astronomy mirrors ancient symbolism. The Great Attractor, hidden behind the Milky Way's dust, recalls the Greek myth of Hades' underworld, a realm concealed from mortal sight yet exerting undeniable influence. Similarly, the Navajo concept of the holy wind, an unseen force binding all creation, finds an eerie parallel in dark matter's invisible filaments weaving galaxies together. These aren't mere coincidences, but evidence of humanity's enduring instinct to explain the unknown through story. What makes the Great Attractor unique is how it bridges these worlds. Like the Norse world tree Yggdrasil, which connected realms through its roots and branches, the Attractor anchors our local group to vast cosmic structures. Its gravitational pull mirrors the Maori legend of Tikor, the void that, though empty, brims with latent energy shaping existence. Even the Attractor's elusive nature echoes Taoist philosophy, where the most powerful forces are often those we cannot see, like wind bending grass or water carving stone. Modern cosmology hasn't dispelled these archetypes, it's given them new form. The Attractor's role in galactic migration resonates with migration myths from Inuit to Aboriginal traditions, where ancestral beings charted paths now followed by stars. And just as myths personified natural forces, today we anthropomorphize the cosmos, calling the Attractor a gravitational monster or cosmic siren. This language isn't just poetic, it reveals how deeply storytelling remains wired into our search for truth. Yet there's a crucial difference. Where myths ascribed celestial motions to gods or spirits, science reveals a universe governed by mathematics, a web of cause and effect spanning billions of years. The Great Attractor's pull isn't supernatural. It's the sum of countless galaxies, dark matter, and the relentless equations of gravity. But in that rigor, there's no less wonder. The fact that human curiosity, from campfire tales to space telescopes, has always sought to map the unseen speaks to something timeless. Whether through star lore or redshift data, we're all still tracing the same cosmic currents, trying to understand what moves us. This fusion of narrative and discovery invites us to see the Great Attractor not just as a scientific puzzle, but as a cultural touchstone. It reminds us that every generation looks skyward and asks why the heavens move as they do, and that the answers, whether told in equations or epics, are threads in the same grand tapestry. The Attractor's mystery endures not in spite of our advancing knowledge, but because of it, proving that the universe always keeps one last secret just beyond our grasp. The quest to unravel the Great Attractor's secrets isn't just a scientific challenge, it's an ethical crossroads. Every photon collected by our telescopes, every supercomputer simulation crunching dark matter models, carries a hidden cost, energy, funding, and human effort that could be directed elsewhere on Earth. Consider the James Webb Space Telescope, a marvel of engineering that took decades and billions of dollars to build. While its infrared gaze pierces the cosmic dust obscuring the attractor, critics argue such resources might have alleviated pressing terrestrial crises, climate change, poverty, or pandemic preparedness. This tension isn't new. The same debates surrounded the Apollo missions, but the scale of modern astrophysics forces a reckoning. How do we justify peering into the abyss when so much demands our attention at home? Yet the answer isn't as simple as redirecting funds. Space exploration has always been a catalyst for innovation, spinning off technologies from medical imaging to water purification systems. The algorithms developed to map the Great Attractor's dark matter filaments now help track deforestation and urban sprawl. More profoundly, cosmic research fosters global cooperation. Projects like the Square Kilometre Array unite scientists across continents, bridging political divides in shared pursuit of knowledge. When researchers from rival nations collaborate to decode the attractor's gravitational whispers, they're building diplomatic channels as vital as any telescope. The ethical calculus grows even more complex when we consider our cosmic footprint. The Great Attractor lies beyond any plausible human reach, but our exploration leaves traces closer to home. Rocket launchers deposit particulates in the upper atmosphere, while defunct satellites clutter Earth's orbit. Initiatives like the IAU's Dark Skies initiative aim to mitigate these impacts, proving scientific progress needn't come at environmental expense. Meanwhile, the democratization of space data, with findings from projects like eRosita freely available to scientists worldwide, ensures the benefits of discovery aren't hoarded by a privileged few. At its core, the Great Attractor's exploration challenges us to redefine humanity's role in the universe. Are we mere observers, documenting celestial motions without consequence? Or do we bear a stewardship responsibility, like astronomers mapping the attractor's influence to predict galactic collisions that could one day threaten our descendants? Indigenous cosmologies offer wisdom here, reminding us that many cultures viewed the cosmos as a web of reciprocal relationships rather than a resource to exploit. Modern science is catching up, with frameworks like planetary protection ensuring our thirst for knowledge doesn't contaminate pristine environments, even as we resist treating space as a colonial frontier. The balance lies in intention. Studying the Great Attractor isn't just about satisfying curiosity, it's about humility. Each revelation, from dark matter's distribution to the Hubble tension, underscores how small we are in the grand scheme. That perspective alone has ethical value, fostering a planetary consciousness crucial for tackling Earth's existential challenges. When we peer toward the attractor, we're not just mapping galaxies. We're learning how to ask better questions about our origins, our destiny, and the legacy we'll leave among the stars. The Great Attractor remains a cosmic riddle wrapped in gravitational mystery, a humbling reminder that even in our age of unprecedented discovery, the universe still holds profound secrets. Think about it, this unseen force with the mass of tens of thousands of Milky Ways has been pulling our galaxy toward an uncertain destiny for billions of years, and yet we've only just begun to scratch the surface of its true nature. Every breakthrough, from mapping dark matter filaments to peering through the Zone of Avoidance with X-ray telescopes, feels like turning a page in a thriller where the plot twists keep coming. What makes this enigma so compelling isn't just the science, it's the philosophical weight behind it. The Great Attractor challenges our assumptions about the cosmos, forcing us to confront how little we truly grasp. For centuries, we imagined the universe as orderly and predictable, with galaxies drifting apart in a stately cosmic expansion. Then came the revelation that hundreds of them, including our own, are caught in a hidden current, racing towards something we can't even see. It's as if we've been sailing on what we thought was a calm ocean, only to realize an invisible tide has been carrying us all along. The journey to understand this phenomenon has been anything but straightforward. Early astronomers, armed with rudimentary telescopes, could only guess at the Milky Way's motion. Today, we've charted the gravitational web connecting superclusters like Laniakea and Shapley, revealing a dynamic universe where galaxies flow like rivers toward basins of unseen mass. Yet with each answer comes a dozen new questions. Why does the Great Attractor's pull exceed what visible matter can explain? Could its origins lie in quantum fluctuations from the Big Bang, amplified over eons into a gravitational titan? Or is it part of something even grander, a structure so vast it defies our current maps of the cosmos? Technology is our torch in this darkness. The James Webb Space Telescope's infrared vision slices through cosmic dust like a scalpel, while next-generation radio arrays like the Square Kilometre Array will trace hydrogen gas in galaxies hidden behind the Milky Way's glare. These tools aren't just instruments, they're time machines, letting us peer back to an era when the Great Attractor was just a whisper of density in the infant universe. And as artificial intelligence sifts through mountains of data, patterns emerge that human eyes might miss, hinting at connections we've yet to imagine. But here's the most thrilling part. The Great Attractor isn't just a destination for scientific inquiry, it's a catalyst for wonder. It reminds us that the universe is alive with motion, a place where even the emptiest voids play a role in shaping galaxies. The forces guiding our cosmic journey were set in motion long before Earth formed, and they'll continue long after we're gone. That's the true gift of this mystery. It's not just about solving a puzzle, it's about awakening to our place in a story far grander than we ever dreamed. So while the Great Attractor's secrets remain just out of reach for now, one thing is certain: the cosmos never stops surprising us. Every observation, every simulation, every daring theory brings us closer to a revelation that could rewrite textbooks or reveal entirely new chapters. And as long as we keep exploring, questioning, and looking up, the universe will keep offering glimpses of its hidden depths, one gravitational clue at a time.